fabrication of environmentally friendly plastic bricks represents a significant advancement in sustainable construction materials. The process involves carefully controlling the ratio of plastic waste to sand to ensure optimal brick properties. In recent past research, the replacement and addition have been done with the direct inclusion of plastic waste in shredded form or small particles. Most replacements have been done by volume calculation, and a decrease in compressive strength was observed as the plastic waste increased. To the best of our knowledge, the effect of the ratio control of plastic waste to sand of plastic bricks has not been well examined. Therefore, in this study, the ratio of plastic waste to sand is optimized to obtain the highest compressive strength and density with minimum water absorption rate, where the curing of the plastic bricks will be carried out at interval periods. The objectives of the study are: 1. To fabricate plastic bricks at different ratios of plastic waste to sand. 2. To investigate the effect of the ratio control of plastic waste to sand on the compressive strength, density and water absorption capacity. 3. To examine the effect of curing time at an interval period on the properties of plastic bricks. The scope of the study includes: 1. Shredded plastic wastes are mixed with sand in a binder, i.e., cement. 2. The ratios of plastic waste to sand are varied, while the percentage of cement is fixed. 3. The curing process of the plastic brick samples is set to 7, 14, 21 and 28 days. 4. Water absorption and compressive strength are carried out on the samples at every curing time interval. A shredded machine was used to shred the plastic waste. Plastic bricks were produced at 2 different ratios for plastic waste, sand and cement. The percentages of plastic waste and sand were taken on a weight basis, but the water was taken on a volume basis. It was done to get a homogeneous concrete to cast on the small mold. The sample was kept in the mold for 24 hours until it dried. After drying, all the samples were taken to determine density before curing. Afterward, samples were put in water for 7, 14, 21 and 28 days to study their water absorption and compressive strength. Figure 1 shows the as-prepared plastic bricks, with a ratio of 75:25 plastic waste to sand and cement. Figure 2 shows the as-prepared plastic bricks, with a ratio of 35:65 plastic waste to sand and cement. Figure 3 shows the curing of the plastic bricks in water. The weight of the dry plastic brick was taken, W1. After that, the dried plastic bricks were immersed completely in a plastic container, containing clean water for 7, 14, 21 and 28 days at a room temperature of 27 plus or minus 4 degrees C. The wet plastic brick was removed from the plastic container at the interval curing time. The extra water from the brick was removed, and then the weight of the saturated brick was taken as W2. This test was carried out to determine the water absorption by the plastic bricks. Standard bricks cannot tolerate water more than 12% of their weight. A small amount of water absorption is needed to avoid cracks or defects. The universal testing machine determined the compressive strength with a capacity of 1000 kN and 0.1 kN, respectively. The compressive strength is calculated when a material can withstand and tolerate maximum stress without fracture. The compressive strength test is the primary test to find the compressive strength of the plastic bricks. The percentage of water absorption of various plastic bricks is presented in Figure 4. It showed that the percentage of water absorption increased with the addition of plastic waste. The variations were mostly due to the increased porosity at a higher percentage of plastic waste materials in the brick block. The presence of plastic waste in concrete aggregates changes the structure of aggregates in 2 ways. One is the change in the porosity of the concrete brick, and the other is the altering of the aggregate structure. Figure 5 shows the compressive strength of plastic bricks, determined after water emergence at 7, 14, 21 and 28 days, respectively. The yield points for different percentages were recorded in the range of 8.88 to 21.54 megapascals after 7 days and from 13.38 to 34.85 megapascals after 28 days. It was found that the compressive strength was very much dependent on the percentage of fine plastic waste in the brick blocks. This is because, generally, the volume of cement is lower than the volume of plastic waste in a unit weight. The percentage of the recommended compressive strength of clay brick is 20.20 megapascal. It was observed that the compressive strength of plastic bricks decreased with the increasing percentages of plastic waste in the block. The plastic bricks containing 35% plastic waste showed better compressive strength than the standard value. It was also found that plastic bricks, containing higher percentages of plastic, 75%, showed lower compressive strength. The results showed that plastic bricks produced by plastic waste could be used as an alternative to soil bricks. It was found that the compressive strength and density of the plastic brick decreased with the increasing percentage of plastic waste in the aggregate. Therefore, plastic bricks containing higher than 35% of plastic waste should not be used as load-bearing materials. However, plastic brick containing higher than 35% of plastic waste could be used as ornamental brick, meaning low load-bearing brick. The novelty of this study are: 1. Alternative to soil bricks, plastic bricks can effectively replace traditional soil bricks, contributing to sustainable construction practices. 2. Compressive strength and density. The study highlights that the compressive strength and density of plastic bricks decrease as the percentage of plastic waste increases. The study demonstrated that plastic bricks made from plastic waste can serve as an alternative to traditional soil bricks. The findings indicated that as the percentage of plastic waste in the aggregate increased, the compressive strength and density of the plastic bricks decreased. Consequently, plastic bricks with more than 35% plastic waste are not suitable for load-bearing applications. However, these bricks can be effectively used as ornamental or low load-bearing bricks. This study was presented at the 7th International Antalya Scientific Research and Innovative Studies Congress held on May the 11th to the 13th, 2024, in Antalya, Turkey.